Hi, everybody. Today we're going to be working on exponential functions. And so we're going to take an awful lot of the expressions that we've been working with for the past few days, and we're now going to look at those as a function of y. So what you'll notice on the screen is one of those functions that we addressed way back in Unit 1. There is our good old exponential function. You'll notice the equation, y equals 2 to the exponent x, and you have the matching graph to the right. I'm going to just change that equation now so we can see it as a table of values, just to be able to examine all the key values that make up that function. You'll notice that we have a y-intercept of 1, and that's because when I put an exponent of 0 on 2, then I get a value of 1. And very quickly, if we start to put positive exponents on there, you start to get your graph to increase. If I was to extend that graph, for an x value of 3, you get a y value of 8. I would double it. And every time I continue to double that graph, my graph or my function value is going to increase really quickly. Notice I'm doubling from 1 to 2, then doubling from 2 to 4, and so on and so on. And so if I was to zoom out right now, you can see that that graph increases very quickly. On the other side of things, I would like you to notice that we have a slightly different relationship. As I take a look to the left of that y-intercept of 1, that would be me putting a negative exponent on 2. Then I notice that my graph is going to decrease. Now, I want to be very clear here. My graph is increasing the whole time because I always read my graph from left to right. However, if I was to move from an x value of 0 to an x value of -1, then I decreased on my x-axis. That movement means that I take half of my value now. And if I take half of 1, then I'm going to get a half. And if I take a half of a half, I get a quarter. And you can maybe see then why that graph is going to extend off to the left. As a reminder, we can always take half of a value, and that's why we see our graph approaching the x-axis. Now I'm going to zoom in really, really carefully here, because it almost looks like, for instance, way down here at an x value of -20, that my graph for my function is on the x-axis. But if I was just to see what is the coordinate of that point, and try to zoom in and zoom in and zoom in, you might notice that I don't have a value there. So if I went back to check into my table and say, what's the value of that function at an x value of -20, you'll notice I get a really small value because of that negative exponent in scientific notation, but I don't get 0. My graph will never get down to a value of 0 because I can always take half of something. There is a basic function for us, and that is us just taking a look at our normal table. So if I was to relatively quickly go back and examine just what is our basic function, you'll see this curve here. There was our original curve, kind of in our original window. I want to focus again, just one more time, on our y-intercept, because there's another important feature of an exponential graph. That if I was to examine everywhere to the right of y equals 2 to the exponent x, I'm going to notice that as I zoom out, I can really see that that value becomes a hard turn for my graph. Now, what I mean when I say that hard turn is this is going to be going all the way back just to our base function. I want to eliminate all the points on that graph. What we do is on the right side of my y-intercept, I'm going to have my graph increasing very quickly through the action of doubling and doubling and doubling. And everywhere to the left of that y-intercept, my graph is going to be very flat. So one side very steep, one side very flat. That makes that y-intercept a very hard turn. It doesn't look like a hard turn there, but if I was to zoom out, you guys might be able to see why it almost looks like it's 90 degrees. We can see that it's not 90 degrees. It's actually a very smooth curve. So I want to jump very quickly then and just start going through and substituting in some different exponential functions to try to examine what are we dealing with then in terms of functions. So for me to pull up my keyboard, I now have 3 to the exponent x. And you'll notice that we get a graph that looks very similar. Y equals 5 to the exponent x. Again, very similar. However, you'll notice that that blue curve, 5 to the exponent of x, is steeper than the red curve, 3 to the exponent x. If I was to continue on and make the base of that value even bigger, we continue with an even steeper graph. Hopefully we can see that as the base value becomes larger, my graph becomes steeper. If I was to then eliminate all of those graphs and examine, well, I've made my base a 2, a 3, a 5. What happens if I make my base smaller? So this time what I'm going to do is I'm going to incorporate a base of 1/2. And you guys will notice that something important changed. My graph is no longer rising to the right, but it's now falling. That should make sense to us because you'll notice that as I allow x to become bigger and bigger, I am now putting a larger value on my fraction. So for instance, an exponent of 2 now means I have 1/2 times 1/2. There is my 1/4, or 0.25. Now, is this a common feature? Well, if I was to go through and now change, well, what if I had 1/3 as my function? The exponent x, now I'll notice if I just change the color of that graph, I see the same feature. Maybe more importantly, I notice that key feature that I still always have a y-intercept of 1. And if I was to then say, okay, well, I'm going to make the base of my graph really small, like how about 1 divided by 20? Well, if I make that base really, really small, well, then we happen to get a really, really steep graph. And if I change that color so we can tell the 3 of them apart, then you'll notice that the same thing is true as what we found before, but in the opposite direction. That now, as the base of my graph goes from 1/2 to 1/3 to 1/20th, as I make the base of my graph smaller, my graph becomes steeper. I think we need to take all of that we've just discovered, and I think we need to sum it up. And so you'll notice that as we played around on Desmos, we had all of our functions that took the form y equals b to the exponent x. All of those functions were y equals a single power. And so what were some of the common properties? Well, the first thing we notice that we had a y-intercept of 1. Every single one of those graphs go through the y-axis at 1. Why? Because if x equals 0, any base to that exponent 0 is going to give you 1. Second key property, we have a horizontal asymptote. And hopefully we can remember back to Unit 1 where we examined all of our key functions that we have a horizontal asymptote at y equals 0. It runs right along the x-axis. Our domain and our range were the same for all of those graphs. I can sub in anything for my exponent. But regardless of what I sub in, if the base of my power is positive, my result will always be greater than 0. Now, we had one other kind of key property, but it's something that kind of depended on what your base was. So if we were to take those common properties and kind of break them apart, then one instance we may have found is, what happens if my base is larger than 1? We would have found that we had an increasing curve. And alternately, if my base was positive but less than 1, then we found that we had a decreasing graph. There's my key properties, and that's what I need to make sure that I know with regards to my exponential functions. Now what I'd like to do is I'd like to jump in and look at a third type of function, because you'll notice that I use the term positive with regards to base twice. The base of my exponential has to be positive. And as we jump in, I want to examine what happens if we go through and we now make the base -2 as opposed to a +2. Right now, what you see on the graph is y equals -2. And so we notice that we have a horizontal line along y equals -2. But if I was to now put an exponent on x of that, you'll notice your function disappeared. Now, maybe we might be able to understand why all of a sudden I don't have a function. But I'm going to go through and show us what that looks like in our table of values again. Because really what's there is a series of points. And when you take a look at those points, you'll notice they're all over the place. Take a look at your table, and you'll notice that, well, when I sub in a 0 for my exponent x, I get a y value of 1. And if I sub in a 1, I get a y value of -2. And if I sub in a 2, I get a y value. But then if I sub in an, we're getting all these values that seem to alternate from positive to negative. Now, why can I not connect my curve from that y-intercept of 1 down to that value at 1, -2? For me to be able to connect those 2 points means that there must be a point in between them. And so if I went exactly in between them, and I want to examine what happens if I have an exponent of 0.5, you'll see in our table that we get an undefined. I'm hoping that as we take a peek at that, we might register for why that's undefined. Ask yourself, what is an exponent 1/2? It's a square root. And if it's a square root, then can you take the square root of -2? No. We should then see why we cannot connect 0, 1 with 1, -2, which means that we get all these separated points, and therefore we do not have an exponential function. So what's very important for us as we move forward is we need to remember that the base of every single one of these powers must be greater than 0. Okay, let's jump in and let's take a look at us examining, and we're going to jump pretty quick. And we're going to look at a really complex function for us. Now, as you examine that function, I'd like you to take a peek at the big, ugly equation on your screen. We've made that about as ugly as you can make it, as ugly as we'll see it. When you look at that equation, you have a bunch of things in that equation. We can recognize that it's an exponential equation because you have your variable and your exponent. But now we're multiplying that function by 4. Up in the exponent, we're subtracting 3. And then we're adding 1 to whatever that value is. I want to do a quick and very quick review back in dealing with Desmos for us to examine all those key functions. So I'm going to go back and put on our basic function, our y equals 2 to the exponent x. There's our exponential graph, and that's one that we want to have in our head. We know that it has a y-intercept of 1. That's our hard turn. We know that that graph would be increasing because the base is larger than 1. We know that it has a horizontal asymptote at y equals 0. And we know that its domain is x is anything, and its range is y must be greater than 0. If I start to manipulate that function now and go back and tackle some of the stuff that we examined back in Unit 1, I can start to transform that curve. Like perhaps maybe I add a 5 to the end. You can see that we have now increased our curve. We moved it up 5. If I was to go through and instead subtract 5, you'll notice we've decreased our curve by 5. We've moved it down 5. That action on the end represents my vertical shift. If I was to take that and then jump up into the exponent and say, but up in the exponent, what I'm going to do is I'm now going to add on 5. And maybe you can see that our graph has moved to the left 5. If I was to then say, let's subtract 4, you'll notice your graph has moved to the right of 4. If I was to get rid of that exponent and say, okay, I'm going to deal with that exponent just in basic terms, but now I'm going to put a negative out in front. You notice that we have now reflected our graph across the x-axis. I could then also work through and say, well, what if I'm going to multiply that function by a value of 5? This one's a little tougher to see at times, but if we recognize that our y-intercept is no longer the hard turn, we might be able to see that that graph has been vertically stretched by a factor of 5. If I was to then multiply that by a value less than 1, like for instance 0.25, then you'll notice that my graph has now been vertically stretched by a factor of 1/4. So all those transformations that we worked with in the past come back to play now. And so if we look at this uglier function, we should be able to look at all the things attached to the power of 2 and examine those as transformations. First off, we're multiplying by a 4 on the outside. That is my vertical stretch. I know that by multiplying by 4, I am going to make my graph steeper. That -3 on the inside of my exponent, inside being horizontal, means that I need to shift my graph because of the subtraction to the right. And lastly, my +1 on the outside of the function, outside meaning vertical, means that I am going to shift my graph up. And so if I examine all of those key features and then the transformations to my graph, I should be able to find a bunch of the key properties for my function. So as I begin to examine my y-intercept for that graph, I know for all base graphs, I have a y-intercept at 1. And so if I look at all those transformations to my curve, if I'm going to vertically stretch my graph, then that will affect my y-intercept. And so my y-intercept would then go from 0, 1 to 0, 4. If I was to go through and shift my graph, well, that's going to move my graph to the right. And as soon as I move that graph to the right, notice it is no longer my y-intercept. So, key feature for us is, yes, we can interpret all of those features to our graph as transformations. However, we should be able to algebraically find a y-intercept. How do you find a y-intercept? To find every y-intercept, sub in an x value of 0. And so we're going to have y equals 4 times 2 to the exponent -3. And now the rest is just us simplifying. So maybe we notice that that's going to be a 4 times a 1/8. That's going to be 1/2 plus my 1. And there's going to be 3/2. Now take a look at number 2. We need to go through and figure out the domain and range. This is where transformations are going to be important. So I know that my base domain is x can be anything, and I know that my base range is that y must always be positive. And so if I begin to examine all those transformations, then if I take that x can be anything, and then I vertically stretch it, and I shift it to the right, and I shift it up, that won't have any impact on my domain for my transformed function. X can still be anything. And you notice that because you could replace the variable x in your original equation with any value and still be able to calculate. My range is where my transformations come into play. For my base graph, I know that y must always be positive. Now, if I vertically stretch where y must be always positive, then I'm still going to get y is positive. If I shift all my y values to the right, then my y can still be anything. But now when it comes to my range, I'm going to take my whole graph and I'm going to shift it up 1 unit. So before, y had to be greater than 0. Now, y must be greater than 1. You might be able to see that feature a little easier if you consider part 3, the equation of the asymptote. My original graph, every exponential, has an asymptote at y equals 0. And so if I take that horizontal line and I vertically stretch it by a factor of 4, well, since it started at 0, it's still going to be at 0. 0 times 4 is 0. If I shift a horizontal line to the right, that will have no impact. But if I shift it up 1, I'll get to my new asymptote. Notice those last two properties. And I'm just going to cross out the blue to remind us that those were for our base function. That if I can examine the transformations to my curve, I can find those key properties of a pretty ugly function. Lastly, take a look at part 4. For me to examine part 4, that means that I need to go through and see what is that function doing, increasing or decreasing. And that relies on me then noticing what does a base 2 exponential function look like. And as soon as I notice that that base is greater than 1, I know that my graph is increasing. Now, does vertically stretching an increasing curve change its direction? No. Does shifting an increasing curve to the right change its direction? No. Does shifting an increasing curve up change its direction? No. And so none of those transformations would change the direction. Therefore, my graph is still increasing. You might wonder, well, then what transformations would change my graph? And I just want to draw to your attention what it would look like if that had have been a negative 4 out front. That negative would now reflect my curve across the x-axis. And if I was to take an increasing curve and reflect it across the x-axis, that would now make that graph a decreasing curve. So watch out for that. Lastly, we're going to go through and we're going to produce a sketch. And I need you to understand that we're not producing a formal sketch. That's what we're going to work on tomorrow. What we want to examine today is, can you take those key features that we just have and can you produce a graph? So first thing we can look at, part 3, we have the equation of the asymptote. So that means that I have a horizontal line across at y equals 1. You also notice that you have a y-intercept at 3 halves. So if you're 1, 3 halves, might be right there at 1.5 or 3 halves. And your curve is increasing. And so we draw an increasing curve up through our y-intercept with arrows on the end. And there you go. So I know we went through some stuff pretty quickly today. Please feel free to go back, watch some sections again, take a look at that Desmos, and play around on Desmos if you like to see some of those other patterns. Okay, your job now, jump into that worksheet, get as much practice as you can. Good luck.